Hello, my name is Cole Fuerth, and for my Capstone project, I made a control system for an electric motorcycle. Please note, the reason this front section of the vehicle is unfinished is because the motor and controller that are the basis of this system did not arrive due to shipping complications. The speed proximity switch is also unmounted because it belongs on the caliper, but this caliper needs to be replaced. As shown, the motor contactor will not engage until the safety switch has been detected to be off at least once since startup. The bike will also not enter gear unless the throttle is at idle and the kill switch is on and there are no level 1 faults. The fault must be cleared and throttle will be set to 0 before trying to re-engage the gear. For the purposes of this demonstration, the drone motor will idle to signify that the bike is indeed armed. The bike can be taken out of gear by pressing the start push button again, or by flipping off the kill switch. This system's main safety component is a motor contactor solenoid, which while closed can be opened at any time by either the processor or by the operator via the kill switch on the handlebars. Here, it is demonstrated that the processor will pull the contactor in the event of any level 1 fault. This example of a level 1 fault is if either side of the handlebar controls are disconnected from the processor, it will pick it up and open the contactor. Whenever a level 1 fault is detected, the fault must be cleared and the kill switch must be opened and then closed again before the motor contactor will once again close. Additionally, there is a fully functional light system, including hazard lights, right and left turn signals, and a horn, although the horn is not attached at this moment because the vehicle is indoors, but the relay does actuate. Both the rear and front brake switches actuate the brake light relay. The Nextdyne HMI has 4 screens. This one is the main screen. It has an alarm window, analog values with bars, a speed indicator, and an in-gear, out-of-gear indicator, as well as a clock. It also has fog light and bright indicators that change when those lights turn on and off. This is the alarm window. It shows the top 10 active faults in order of their priority. If I disconnect the left handlebar Ethernet, it will throw a fault. To clear the fault, I must reconnect the Ethernet and then press fault reset to clear the faults. Up next is the statistics screen. It has an area for proprietary values, including the battery voltage and current power draw. It has individual cell voltages, throttle in and out, and shunt readings. So far, the only settings on the settings screen are performance settings. To maintenance the vehicle, first remove the seat screws, remove the seat, tilt back the tail fin, and then remove the wing nuts on each panel to reveal the control panels of the vehicle. There are 3 main control panels on the vehicle. The first houses the main processor and isolated inputs. The second manages analog signals in and out. And the third manages power distribution, fusing, and current measurement. A system has also been designed and implemented to charge all of the battery packs at once. I will demonstrate with one. First, we need a supply. I will also use a dongle to split the supply off. The XT30 connects to a 5-volt regulator, which will activate all of the relays attached to all of the cells. This switches the cell configuration from a 16S series to a 4S parallel configuration. Now we can plug in our lithium-ion charger and connect it to the charging port on the battery pack. After picking the settings on our lithium-ion charger, we're ready to charge. And that is my third year Capstone project. Thank you for watching.